Switching on 3, 2, 1. Hello everyone. Recently I got to contribute a new utility to TorchVision, and that's this feature extraction utility. This video is going to explain how that works, and with some code we'll go through some examples. I'm assuming that if you've come here, you know what feature extraction is in general, and why we would want to do it. And just to get us on the same page, some examples of feature extraction is maybe you want to visualize the feature maps from ResNet 50 when you feed in a picture of a cat, for example. Maybe you want to extract features from lots of different images, combine those features in a certain way, and compute image descriptors. And using those image descriptors, you can, then figure out how if two images are similar or dissimilar, and then you can do tasks like facial recognition, copy detection, image retrieval. And those are two examples where you're using this model in evaluation mode, but you can also train a model. So, for instance, you take and this is the example down here, you take like a ResNet 50 backbone, and you extract features, you extract the 4 main layers of it, and you feed those into a feature pyramid network. And then with that, you wrap that in mask RCNN, so you add the detection heads onto there. And then you have a model which you can train end to end, so backbone included, with object detection and segmentation. And the whole motivation for having feature extraction is because normally when you do things like this from scratch, you might actually write your code such that it's easy to be able to get at the feature maps of interest. So you'll actually write your forward method in your PyTorch module such that it gives you back the feature maps. But in situations where you don't have total control over source code, or you coded it before without thinking that you were going to use it for these reasons, or you just want flexibility, feature extraction is the way to go, because you can have a model that's already defined and get at the intermediate features without actually having to reconfigure the source code. And that's the whole point. I'll show you how that works. In this video, I'm going to explain what FX is, which is a core PyTorch utility, and then how that relates to feature extraction. And then you'll understand, you have the knowledge required to understand the next steps. So the next steps, I'll give you an example of extracting feature maps for ResNet. I'll also look at getting out attention maps for xcit, which is a vision transformer model, one of the more recent variants. And then last of all, if you've worked with feature extraction before, you may have used hooks to get features out. So I'll show you, I'll just explain why this FX-based feature extraction is a lot more flexible than using hooks in many instances. So why you would use this instead of using hooks. So to start with, torch.fx, if you go to the documentation, actually I forgot to mention, to see this documentation right now, 15th of September 2021, and for a little while thereafter, you need to go to the main branch, not the stable branch of the documentation, and then go down to feature extraction. Anyway, where was I? TorchFX. So this is a normal PyTorch module here, and so you can see that in the init we make some parameters. We also initialize a linear or a fully connected layer, and then in the forward method we do a few things. So we take in this input, and then we add the param. We apply we pass it through the fully connected layer, and then we do this clamp and we return it. So a couple of things happen in this one line here, and this module could be a lot more complicated, and there could be a bunch of sub modules that are nested within nested and in other files. And the idea is I want to get at something specific. So I want to get out of this x plus self param. I want to see what that looks like. It's a weird thing to want to do, but this is just a simplified example. So if I wanted to do that here, I'd probably have to just rearrange this code and return both things. But there's a way to do it with this new utility where you don't have to do any rearranging at all. And you can leave the source code as it is. So what fx does is it does something called symbolic tracing. So it symbolically traces the code here. That means it goes through step by step and looks at what's happening or what operations are happening one by one. So when Python looks at this, by the way, Python will pass this and go, okay, I know that this is happening first. It has its rules for order of operations. And then this happens second. Then this clamp happens third, and then the return happens last, right? And then so symbolic tracing steps through that process step by step, and then it let me draw this for you. So it has like an input node. It goes, okay, there's an input X. This is an input node. So nodes have types, and then there's like an add node, and I think this is a call function node. Well, it's a type of node, and then there's like the linear, right, and the linear transformation, and then there's the I think there was the clamp and the return, right? So now it's like unraveled all of this into step by step, and then all these nodes will have like string identifiers in the feature extraction, right? Which I'll show you how to get at. And then if you wanted this node, for instance, you could say, okay, I want to extract, and then you look at the identifier of that node, and I want to extract that node, so you'd get this out, basically, right? And then, so the reason this is called a graph, by the way, is because it doesn't have to be linear as well. So in ResNet, for instance, you could imagine, because you have that skip connection, then you'll have a bunch of nodes that do this, and then you'll have one which goes like this because of the skip connection. And there's all sorts of other, it can fork and take whatever path. But the idea is that you have nodes and edges connecting them, and it's not necessarily linear. So we're going to call this a graph. So what fx does is then it has a graph representation. You can print that. This is not very easy to interpret, but there's also like a tabular version of that. So look, these are the types of nodes. So there's a call function, which is the add, the call module, the linear. This must be from another example because now there's a relu there as well. And then you've got arguments to each node. So that kind of specifies the connectivity between nodes. So that's the symbolic tracing part of fx. And then the other thing that fx does is it then reconverts that back into a forward method, which is equivalent to the forward method that you put in. And this is actually Python code. Like, you can run this. It's just a little funny because you have two things happening on one line separated by this semicolon. So I'll let you look at that after. But this is Python code that is just like any other Python code, and it's just broken this down into those steps that I mentioned before, right? So one operation per line. And then so this is exactly what feature extraction uses. So if you look here, it provides this create feature extraction extractor function. And what that does is it uses fx to symbolically trace the model, gets that graphical representation. And there's another utility called get graph node names, which I'll show you in a sec. And so you can look at the node names, and then you can pick which ones you want as outputs. So the user selects outputs, and then torch.fx allows you to actually manipulate this graph. So that's the whole point of this process here, by the way, is like you get this intermediate graph representation. You can manipulate nodes in this graph, and then recompile it and reproduce the code. So what this feature extraction model does is it does that, except what it does is it, say you pick, again, going back to this example, say you pick this node and this node is what you want out. So the feature extraction will get the graphical representation. It will set these as output nodes. So it will set this as an output node instead. and an output node, oops, not that one, this one, it will completely remove any nodes. So if there were more nodes, it will completely remove them because it knows that you don't want anything else from after this one here. And it will remove any parameters associated with them as well. And then you'll be left with just this. And then it will turn that into Python code, which returns these two in a dictionary. That's the whole idea. So to summarize again, trace through your module, turn it into a graph. Based on what you asked to be return nodes, manipulate that graph. So get rid of any dead code that's not needed, get rid of any and their associated parameters, and then return those two, and then turn that into a forward method, which does exactly that. So I believe that explains, what FX is and how it relates to feature extraction. And you can look at, there's plenty of documentation on FX, and it's interesting stuff, and you can look more into it. But for now, I'll just focus on the feature extraction bit. So let's do some examples. So I'm going to use the PyTorch image models library to create a pre-trained ResNet model, ResNet 50. Put that in eval mode. I'm going to prepare some images. So by the way, I'll provide you with this code. I have some utility helpers here to try to separate the non-feature extraction stuff from the meat. But so this is also boilerplate. So I just load up 4 different images, make sure to resize them and crop them. And here they are. And these are all from ImageNet, by the way. And just to make sure that I've set everything up correctly, I'm going to take one of these images, so this first blue jay here, I'm going to prepare it using my prepare utility, which just does normalization and turns it to a tensor, and then put it through the model, and then see if I get 17 out, which from a lookup table that I've got on the side, that corresponds to J, right? So let's see. Okay, so everything's working as expected. Now for the interesting bit. So as I mentioned before, we have this this utility called getGraphNodeNames. And so I can put that model into getGraphNodeNames, and it will do that whole procedure that I mentioned before, except it won't specify any output nodes because I haven't specified what I want to return. So it will actually just return the default return node, which is the same output as the original model. But it actually creates that model, but it doesn't give it back to you. What it gives back to you instead is the node names. So it gives you train nodes and eval nodes. Now, just as a side note here, why does it give you 2 sets of node names instead of 1? And it's because you could do model.train. There are 2 modes for PyTorch modules. There's train mode and eval mode. And it's sometimes possible that you have something like this, self.training. If self, inside the forward method, you have something like if self.training, do something, and else do something else, right? So it's possible then that when you actually do this tracing operation that I mentioned before, when you go through the operation step by step, that they differ for train mode versus eval mode. So that's why I return 2 sets here. Now I know particularly for ResNet 50, in a lot of cases, train nodes and eval nodes will be the same. I just use this line to double check that for myself, and they are the same. And then I have a look at what the train nodes are. So look, this is that input node. This is the first convolution, the first batch norm, first activation. Then there's a max pool, and then it goes into layer 1 and all the stuff that happens in layer 1. Right, and in layer 1, a lot of different things happen, but eventually this is the last operational last node that relates to layer 1, and then you have layer 2, 3, 4, and then you have your final global pool, your flatten, and then your final fully connected layer, and then your output, right? So it's what we expect. So what we would do here now is say, okay, I want the outputs for feature extraction. I want to see the outputs of the different layers. So we can use, let me go over to it, grab the code for you. There we are. Ignore the bottom for now. So we can specify that I want to return these nodes. Now, I've taken a bit of a shortcut here because, technically the name of the node that I want is this. So I could put this here. But create feature extractor is helpful in that if you provide like a truncated name like this, it will just go backwards through all the nodes and it will pick the last one that has that as its parent, right? And so you just need to be sure that the last node is the one that you really want. And so if you know enough to know which features you want, then you probably know enough to know which node it is that you want. Right. So to create the feature extractor, then it's similar to the get graph node names, except the difference is, so I do feed in the model, but now I have to feed in the return nodes. And what it gives me actually is a feature extractor. And this is, is instance. So this is just a torch module, PyTorch module, right? It also happens to be, so then this is also a graph module, which in turn is graph module. There we are. Which in turn is a type of torch module, right? So there's quite a lot of inheritance happening here, but at the end, this is just a PyTorch module, right? And so we can, in the same way that we would with a normal model, we can feed the inputs into it. So we'll feed that first blue jay picture into it, and we get an output. And the output looks like this. It's a dictionary, and the keys are actually the names of the nodes that you fed in, right? And so if we look at out layer 1, let's look at the shape of that instead, right? So this is what we expect. We have a batch size of 1. We only fed 1 image in. We have 256 channels, which if you know ResNet, that's right. And then the image input size was 384 by 384, and the reduction is 4 at layer 1. So that's right. So 384 divided by 4 is 96. We can verify for the other ones as well that the shapes are what we expect them to be. There we are. Oh, I have to print this. There we are. Right. So then I can actually go ahead and, you can read this code later if you want, but I plot out 4 randomly selected feature maps from each of those layers. So for reference, the input image, layer 1, and the resolution. So these are all from layer 1, just randomly selected, and the resolution of them. As we expect, you can still see the outline of the bird, and actually you can see like certain features accentuated, like edges are accentuated here. For instance, here it seems that blue maybe is accentuated. And then as you go deeper, you start to lose the bird, but it's still there. And as you go deeper, these get more and more abstract. And then towards, the deepest layer 4, you have highly abstract, and you can't tell it's a bird anymore, and quite sparse. So there we have it. That's feature extraction with ResNet, and with no rearranging of the source code whatsoever. So before I moved on to the xcit, I just wanted to show you some other properties of feature extractor. So remember, it has a graph, which you can print, and you get this, but you can also print tabular, and you should have done this. to make that work, by the way. I think tabula or tabulate. Yeah. So let's have a look at that. There we are. So look, you have all the nodes, and nodes aren't, I know I am printing nodes here, but I'm actually just printing the names that that the nodes have. And but here is like, nodes themselves. Node is an actual object in torch.fx, and it has different types of properties. So it has the type of node that it is, the name that torch.fx gives it, and I'll actually, that's another point I should talk about in a second, and the arguments, and you can look more in detail at that when you have a look at the torch.fx documentation. But actually, I did want to focus on the name for a second. So even here, I think what's written here is not the same as the name that comes out of the TorchVision utility. So I've made these names, I've tried to design them such that they really stick to the principle of following. Like, so there'll be a submodule, a submodule in ResNet which is called as a class attribute layer 1, and then that's in a module list. So there'll be there'll be blocks within layer 1. So there'll be the 0th block, the first block, and then within that there'll be the activation or the convolution. So this is like a dot separated path from the top level module down to the leaf operation or leaf module. Okay, so moving on to the xcit example. So with xcit, let me just, here we are. So we can create a different model, right? Which is this xcit from Tim. It's pre-trained. This may take a while to download when you do it. Put it in eval mode, prepare the inputs, and forward it through the and forward one of the inputs through the network, and check that it comes out as expected, just so I know that I've set everything up correctly, just as before. So we feed in the blue J, which is the 0th input, and we hope to get 17. Yeah, perfect, 17. So everything's working as we want. And now again, we can get the graph node names as we did before. But so symbolic tracing isn't perfect, right? Which is the next point I want to make. It's not perfect. You can't trace through every type of code. For instance, we already know that from the fact that we use train nodes and eval nodes, that discussion that I had before, that if there's like control flow, well, the tracing is only going to go through one branch of the control flow. It won't check both, right? So that's why we trace in both train mode and eval mode. And then so what's happening here is that this is a completely different problem. Symbolic tracing is not able to handle a range. And then you can look in the FX documentation to understand exactly why that's happening. So let's find where this is happening. This is happening in the forward method. So there's an A range in the forward method, line 118 of xcit. And now I've got the source code for xcit up. Here it is. What line was that? Line 118. Let's go there. Here it is, A range. And then this is in the positional encoding. Now, I said before that I want to get at the attention. I want to look at the attention maps for xcit. That's what I care about. So I don't really care about anything that happens here because I'm not trying to extract any features from this module in particular. So what I can do is I can treat this as a leaf module. And so remember, we have this, like when we specify nodes, we have this dot separated path from top level module down to the leaf module, right? So if we try to trace through this, or leaf operation, if we try to trace through this, one of our nodes would be this A range. But if we want, we can treat this whole forward method as one node and just kind of package all of this into one node. So we're treating it as a leaf, right? Why am I saying leaf, just in case it's still not clear? So you can imagine, like, you've got this xcit class here, right? Which is the top level module. And then that, creates an xca block and a class attention block. And it creates all the, so class attention block, we can look at the definition of that, for instance, right, which is up here, also in the xcit file. So we might say, okay, this creates like a xca block, and then like a class attention block, right? And then those might make use of other submodules, and those might make use of other submodules, right? So this is a tree. And eventually we get to a place where we can't subdivide into smaller units, so that's a leaf of the tree, right? And so when this symbolic tracing happens, it actually goes, leaf to leaf to leaf, step by step. But if I want, I'm able to treat this as a leaf and just say, don't trace within xca block, treat that as a leaf. And so when you write a node for that, you make that a node which is a core module node, and you're calling the xca block module. And that just means I don't have to deal with any of the issues that might arise with symbolic tracing within this part of the tree. But it also means I don't then have access to be able to extract features from within this part of the tree, only the output of the xca block, right? So back to where I was, line 119 here. This is one of these junctions in the tree, and what fx is doing is it's trying to trace within this forward method, and I'm just going to say, you know what, I don't need that. I just need you can just treat that as a leaf. So here I can specify tracer keyword arguments. Why? Because these keyword arguments are eventually filtered down to fx, the fx tracer, right? And then I can specify leaf modules and a list of leaf modules. So modules that need to be treated as a leaf, right? So I need to import this from tim.models.xcite, import this, and then put that as one of the modules that I don't want to actually trace through. And now this has worked. So the tracing worked. And let me just copy the rest of the code that I wanted. It turns out again that the train nodes and the eval nodes are the same for both the same graph. So this assert statement won't trigger any issues. And I can print the train nodes and have a look at them. Now, maybe you need to know a bit about the xcite model. And there are some good videos already on YouTube for that. I actually won't go for the paper. I'll draw something here. So I want to get the attention maps. So I usually draw these vision transformers bottom up, because that's how they were drawn in the papers. That's how I remember them. So you take your image of a cat, you break it up into grid cells, and then you flatten that out into a sequence of grid cells. And then you go through a bunch of self-attention transformer layers. And by the way, there's a class token here. I'm really just rushing through this because it's not part of the main topic, and that class token gets propagated to the top as well, along with all the patches from the image. And then at the end, there's this attention mechanism where the class token attends to all of the image patches, and then so we form a heat map, an attention weighting map, right? So this will be like a heat map of where the class token. These drawings are bad, but we're gonna go through the actual examples. You see what I mean? So if I then turn this flattened sequence back into a grid like this, there'll be like a heat map of where the class token is trying to attend to, and eventually, okay, so the class token ends up predicting cat, and I want to know what did the class token attend to from this grid in order to predict cat, right? And I'm also familiar with the code, the source code for xcit. Let's see how we would do this. I know what the source code for xcit is like, but I want to give you an example of how you would do this if you just knew enough about xcit to know that you want the class attention. So let's actually look at what this printed out from the train nodes, and let's see if we can find it. And I'll pretend I don't know about the source code. Okay, so you've got your input. We know about patch embedding. We know about positional embedding. So this is not undoubtedly the first transformer block. The second transformer block. Let's just scroll down globally. Okay, 12 transformer blocks, 13, 14. Keep going, keep going. Okay, here we are, class attention blocks. So from the paper, I don't know exactly how many there are for all the architectures, but for this one, we can see that there are 2 class attention blocks. And maybe I'm interested in looking at the second one because it's right before the output. And I want to try to find somewhere where there's attention. Here it is, attention. And I want to find, which of these nodes. I want to make sure to highlight them all. So we're looking at all of them together. Okay. So there's still a lot of nodes even within the attention, and I want to figure out which one's the heat map that I'm looking for. And so for this, I am going to have to delve into the code and make myself familiar with it. But I think this would be the case in any situation where you wanted to extract these features. So let's try to find this class attention. Class. Here we are, class attention block. This should have, okay, so there's a class, so a submodule of the class attention block is a class attention module. So I'm going to go to the definition of that. And this class attention module, here it is, self dot, okay, so here's, so you may need to read through this, and I'm going to use the fact that I know what's happening here. But I know that this line of code is where you matrix multiply the queries and the keys. So the queries are coming from the class token, and the keys are coming from all of the positional tokens from the image. And so this is your attention heat map. And then you apply softmax to that to make it all sum to 1. And then there's a dropout, and then it ends up at some point, multiplying the values from the class token. But I think what we want is the output of this. We could get the output of this, but maybe I want to apply some temperature to the softmax so it's easier to visualize. So we want the output of this one here. So we know it's before a softmax, and that's before some sort of dropout. And that's after some sort of permute. So let's look back here. Here I've just spotted it, softmax. Is it the last softmax amongst the attention nodes? Yes. And then there's a softmax here, there's a dropout after it. So here it is, it's the matrix multiplication. So this is the node we want. So although that seems that it wasn't super easy to do, probably if you wanted to do this, you would know enough to look here. So I've already got that code somewhere. Just going to show you how this is done. We'll need these in a moment. So I'm going to specify the return nodes, but now I'm going to specify it as a dictionary. I can do that as well instead of a list. And I only want one node. And the reason I do a dictionary is because I want the output key to be something that's easier to type. So now instead of the output key being this, the output key will just be this. This is something I've specified. I can make this hello world if I want. And then so I'm going to use my create feature extractor on the model with these return nodes, and remembering to use the trace, the leaf module specification. Otherwise, it's just not going to work. And then I'm going to, I'll comment this out to make it easy. So let's say I want to look at the blue jay. It's the first image from before. I just use this to make it easy to switch. And I want to look at the output of this feature extractor. I'm just going to print the keys for you so you can see what the keys look like. Okay, so it's a dictionary with a single item with attention as the key, which is what we specified above. And I can look at the shape of this. I probably want to look at the shape, not the whole thing. Okay, so what's happening here? This is the batch dimension. So there's only one in the batch, one image. You should know enough about xcit. If you were to do this, you'd know enough about xcit to know that there are 8 heads, 8 attention heads, because it's multi-head attention. And this is that, these are all the tokens. So this is the class token and all the positional tokens. So if there are 2,304 positional tokens, then it's a 48 by 48 grid, which makes sense because we had a 384 input image with patches that are 8 by 8. So that's 48 by 48. So it's what we expect. And then we're just going to do a bunch of stuff, which I won't go through. So I won't go through in detail. So we'll softmax, but with temperature, so we get better visualizations. We'll remove that class token. We'll unflatten this and make it into like a square, which is what we want. We'll reshape it. We'll resize it so that it's the size of my image because I want to be able to overlay onto the image. And then we essentially have our heat maps. So let me just get the rest of the code here. This is just to overlay the heat map, just a bit helpful. So yeah, the reason I wanted to do this is because in the paper, they show this exact thing. So in the xcit paper, they have this picture with these umbrellas, and then they show like the attention heads, 3 of the 8 attention heads, what they're doing. And the claim is that each head seems to represent semantically coherent regions. So this head looks at the umbrellas, this one looks at the faces, and this one looks at the background. So I tried this out with the blue jay. What have I done? I need to make sure to be pulling this key out. Yeah, and this is the attention map. So this is the 8 heads. These aren't different rows representing highly different things. I just have it in 2 rows so we can fit it. This is the original image for reference. These are the attention maps from the 8 attention heads. And then I was, as a side note, not related to particular feature extraction, I was surprised to see all these blotches here. And yeah, sometimes it looks like there's focus on something. Like here, it's focusing on different parts of the bird, but it's not as clear as in the paper. If someone could, give me some insight into why this is happening, that'd be awesome. And just for fun, let's look at another one. So I decided to get, the reason I have these other ones here is because I thought, okay, maybe there's not enough interesting things happening in this picture. So if I have more stuff in a picture, the heads will focus on different things. So let's look at this, the third one here. So the third one, again, it's really blotchy. The corners are really like highly attended to for some reason. But sometimes his glasses are attended to, or like that flag is attended to. More so in this picture, something this 4 is attended to. It makes no sense to me, and it doesn't look like what it does in the paper. So yeah, as a bonus, if someone can comment their thoughts on, and especially this like kind of this checkerboard patterns here as well, that'd be great. Anyway, so last topic before we close this out. You may have been thinking this whole time, if you know about hooks, why don't we just use hooks? I won't explain how to do that because running out of time, and if you know, you know. So some disadvantages of hooks. One is hooks can only be used to grab the output of modules, right? So you can't, even in this xcit example, you couldn't grab the output of, now I've lost it. I know it's here. You couldn't grab the output of this because it's functional, right? We could make a separate module called matmul and make the forward method do this, and then make that into a leaf module. Oh, no, that's for feature extraction. We don't need to make that into a leaf module, but we could make a separate module called matmul, and then we could do a forward hook on that and get the output of it. But that means you have to go in and mess around with the source code, so it wouldn't work. The other disadvantage of hooks is that once you've extracted that map, that attention map, you still do the rest of the operations after the hook. So that wastes time, computation, and memory for parameters. And if the features that you want to extract are actually early on in the module, then you don't want to be doing that. And especially if you're training like a detection model, you don't want every single forward and backward run to be, doing forward pass through parts of the model that you actually don't need. And yeah, I think those are the main disadvantages of hooks compared to, and then the last one is you can't script the model. So for example, this should work. I mean, as long as the original model is scriptable, then this should work. So if I go to torch.git.script model, okay, that works. So then this works. There we are. I'm glad that worked. So, and then with the hooks, there's issues with making it scriptable. So then you can't go ahead and deploy it into a production application. You may have a bunch of other questions, and if you do, feel free to drop them in the comments, and I'll try to answer. But yeah, in a nutshell, that's how the feature extraction works. Thanks for your time.